amplitudes.
Hey. Yeah, thank you so much for the kind invitation and for the announcement. It's a pleasure to be here in person. I'm really grateful for the opportunity to chat a bit with, of course, all the required social distancing. Yeah, in this talk, I'm about to give some overview of various recent papers that are dedicated to mathematical properties of string amplitudes. In particular, I will tell you about so-called modular graph forms, which are non-holomorphic modular forms, as they occur in string amplitudes. And yeah, to a large degree, this is a subject that was invented or co-invented in Paris with a lot of groundbreaking work done by Pierre van Hoof and Boris Gioli. Yeah, and I'll tell you some overview story that came from recent papers in collaboration with Eric Doker, Daniele Dorigoni, Jan Jelken, Martijn Hidding, Axel Kleinschmidt, Carlos Machra, Boris Gioli, and Bram Werdeck. All right, so what is this talk about? The key idea of today is to use string amplitudes as a tool to learn about mathematical structures that come from Riemann surfaces. So more precisely, we will look at the integrals over vertex operator insertions in the worldsheet. And we will go through various worldsheet topologies and see what kind of mathematical structures, what kind of function spaces come about. So in the first place, we can distinguish between open string and closed string cases. In case of open strings, all the vertex operators are sitting on the boundary of the worldsheet. And accordingly, you get certain iterated integrals, where iterated means that the open string insertion points will be ordered along the worldsheet boundary. Not sure whether you can see all my head waving. If we proceed to closed strings, then there is no more notion of ordering on the boundary. All the closed string vertex operators want to be integrated over the entire surface. And there you will get certain single-valued functions or single-valued periods, as they're sometimes called in mathematics. And we will, in particular, get modular forms starting from worldsheets of genus 1. And this will be the main subject in the second half of the talk. Good, and how do we get these function spaces from string amplitudes? Well, we need to expand in the inverse string tension alpha prime, or more precisely, we will be doing a simultaneous Taylor or Laurent expansion in the dimensionless Mandelstam variables Sij, written in blue here. And the coefficients in this alpha prime or Sij expansions, these coefficients will be the functions in question, iterated integrals and single-valued periods and functions. So here's a schematic formula for how I think about string amplitudes today. In all cases, you will integrate over the moduli space of n-punctured Riemann surfaces of various genera G. And the most prominent part of the integrand is this exponential here, involving the alpha prime dependent Sij's and involving the Green's function calligraphic G, which is adapted to the surface you're working on. So this is the engine of the alpha prime expansion, and it's of course not the full expression for the scattering amplitude, but it's the backbone of what we will be doing today. So what I'm suppressing is some theory-dependent factor where the polarizations are sitting. Well, it's worth discussing that in a separate talk, but I won't be doing this today. And today, the viewpoint on string amplitude is a mathematical one that we investigate them as a laboratory to learn about some new mathematical structures. And I will completely neglect the more physics-oriented motivation to do string amplitudes. So my apologies for not talking about the specific implications for string dualities. My apologies that I won't be talking about how you get gravity as a double copy from strings. So there are a lot of other motivations to study string amplitudes, and today I will focus on the mathematical one. All right, let's proceed to the name dropping. What kind of periods and functions will I be talking about? And first of all, we were having the symbol calligraphic M for the moduli spaces. Of course, the full homework in computing string amplitudes is to integrate over the punctures, where the vertex operators are sitting, and to integrate over the moduli, namely the complex structure moduli of the surface. And I will be working at fixed complex structure moduli, so I will only integrate over the punctures. And the formal way of saying that is configuration space. We will investigate the periods of configuration spaces, which is the result of integrating punctures. And in the simplest case, you integrate the punctures on a disk boundary. This is open string tree level, where the most general object that you get from these puncture integrals is a multiple zeta value, here defined as a nested sum below. You will see that later on again. So for the moment, this is the overview part. So please don't bother to read all the definitions in detail. So while the open string from the disk boundary gives you all multiple zeta values, the closed string, where the worldsheet is a sphere at tree level, it only has a subset of zeta values for you that adopt the single valued multiple zeta values. And I will motivate these, this terminology and these expressions later. So apart from the tree amplitudes themselves, it turns out to be useful to take a step back and to not integrate over all the punctures. Well, ultimately, you do want to integrate out all the punctures, but let's suppose we do this one step at a time. Integrate over the first puncture, then over the second, and then you maintain functions of the unintegrated punctures. Let's say we are too lazy to integrate over the last puncture, Z0. Then we will get interesting classes of functions of Z0 in the next to last step. In the case of the disk topology, you will get multiple polylogarithms, certain iterated integrals over the log forms, where the logarithms come from the Green's function at genus 0. And in the closed string case, if you are too lazy to integrate one puncture on the sphere, well, you will again get polylogarithms, but everything you start with on the sphere is a single valued correlate, single valued in multiple variables. And if you integrate over some of them, you will maintain single valuedness. So you get a special subclass of polylogarithms that are single valued as you transport Z0 around all the singular points, say 0, 1, infinity. Good. And yeah, I will argue the first part of this talk that it's really essential to know about the situation with Z0 unintegrated. Even though that this is not the final answer, it's a step that carries essential information and it instructs you how to organize the single value multiple zeta values that you have in the final answer. And one of the nice stories that already becomes apparent at tree level, you can get closed string results for free. If you have already expanded your open string amplitudes, if you have all the multiple zeta values in front of you, then there is a formal operation called the single valued map that immediately gives you the closed string result using open strings as an input. So this smells a little bit like KLT, Kawaii-Level-Tai, but it is strongly refined in the sense that the single valued map knows about all the cancellations that are camouflaged by the Kawaii-Level-Tai formula. So this is the situation at genus 0 or tree level, and the second half of the talk is dedicated to genus 1, where things become modular on the closed string side. But before going to these modular forms for closed strings, let's take a look what the open string has to offer at genus 1. Strictly speaking, I'm in charge to draw both the cylinder and the Möbius strip now, but from the mathematical viewpoint, there's not too much new from the Möbius strip, so it's all about cylinders now. So if you do your homework and integrate all the open string punctures on the cylinder boundary, then you get so-called elliptic multiple zeta values. This is a class of meromorphic functions of the modular parameter tau that was studied among other places by mathematics papers of Benjamin Enriquez.
Sorry, can you put some of the points on the other boundary?
Oh yeah, you can do the non-planar cylinder, and it's still true that you get elliptic multiple zeta values. It was somewhat a surprise because we were initially expecting
the non-planar, what do you call this?
Oh yeah, sorry for the jargon. I understood your question as if you want to place some punctures here on the lower boundary.
Sure.
Did I understand correctly?
Yeah.
Okay, so it's at first glance you might expect that you get more general functions of tau if you do so. And if you evaluate the differential equations of that latter scenario, it's still the differential equations of elliptic multiple zeta values. So in short, that space is large enough to cover also the non-planar situation. Even though the picture may look different, yeah. But here you have my word, it's the same function space. Okay. So this is again the scenario where all the cylinder punctures are integrated out. And let's once more play the what if game. If there is one puncture Z0 that you refuse to integrate, then what you get in intermediate steps, what you get from the partial integral of the remaining punctures, is a certain class of functions of Z0 known as elliptic polylogarithms. There are various ways of spanning the space of elliptic polylogarithms, and the one which appears to be most natural in string theory is the description of Brown and Levin of elliptic polylogarithms. Yeah, so this is the open string situation at genus 1, and where I ultimately want to gear towards is what you get from closed strings at genus 1 if you integrate punctures on the torus. So there is a notion of modularity for the torus diagram, and as you integrate all the punctures order by order in alpha prime, then you get a modular invariant function of tau, or you get infinite families thereof. So these functions are known under the name of modular graph forms. So the acronym here is for Doker, Gürdogan, Green, van Hoof, and also another version of them by Doker and Green. Yeah, and in the first place, I will show them in a way that modularity is manifest, the way how they are traditionally described in the literature, including these papers from 2015 and 16. But I will also give an alternative description of modular graph forms in terms of iterated integrals. And the goal is to be as close as possible to the corresponding open string quantities. So the goal is to view these modular graph forms as a single-valued variant of the elliptic multiple zeta values from the open strings.
So do you say it is modular invariant?
About the modular graph forms, I do say that, or that they are modular forms. But the elliptic multiple zeta values are not. These meromorphic quantities from the open string, well, they don't attempt to be modular invariant. You can do a Jacobi transform and how you parameterize the cylinder. So they are part of a, I think, vector with respect to the modular group. But the clue of the closed string will be that you combine meromorphic with anti-meromorphic functions. And it's this combination of both which gives you a notion of modularity. Okay, I hope this will become clearer as I'll go into more details.
You could also consider often closed amplitudes, right?
Oh, really good point. Indeed, yeah. I think there was a recent very interesting paper by Schlotterer in May of last year, where he mapped this situation, one closed string on the cylinder, otherwise open strings, where this scenario got mapped to pure open string amplitudes. That, loosely speaking, a closed string insertion in the cylinder behaves a little bit like a pair of open string insertions on the cylinder boundary. But I won't cover this today. All right, and now you can probably anticipate who is missing in that picture. What if we work on the torus and don't integrate over all the punctures, but we leave one puncture unintegrated? So by analogy with the other cells in that graph, you can probably guess that these are single-valued elliptic polylogarithms. And this is not the way how they were firstly introduced in the literature. Instead, I think the first systematic discussion of these elliptic NGFs was done in a paper by Boris with Doker and Green. They arise, among other things, from degenerations of genus 2. And yeah, they can be manipulated in similar ways as applied earlier on for modular graph forms. And in a recent paper, Doker, Kleinschmidt, Schlotterer, we looked at various mechanisms to generate infinite families of relations. Yeah, I hope that I will have time to talk about these elliptic modular graph forms with an unintegrated puncture Z0, that I will try to convince you that this is the way, a way to span the single-value elliptic polylogarithms. Now, everything here is up to genus 1. Needless to say that we ultimately want to cover all kinds of genera. And indeed, there is some impressive work done on the closed string side, a definition of modular graph forms of arbitrary genus in a paper by Boris together with Eric Doker and Michael Green. And one way of organizing these higher genus modular invariants is to promote them even to be tensors, so-called modular graph tensors. And there you find a proposal in a recent paper, Doker-Schlotterer. All right, so this is the roadmap, and the goal of the rest of the talk is to walk you through these individual cells and to deliver the details and hopefully give a flavor of how all these objects and function spaces are interrelated. Is there any general question about the bigger picture? Okay, so the outline was already implicit in the previous slide, so I won't comment much. But this is a slide where you can later go back to and look up some important references, which I hope to highlight again. Yeah, we start at genus 0. Let's talk about polylogarithms. So this is again about string tree level, where the open and closed string worldsheets have the topology of the disk and a sphere, respectively. And there, the Green's function is as simple as a logarithm. Remember, the alpha prime expansion means we integrate an exponential of alpha prime times Green's functions in all pairs of points. So what do we get by integrating logarithms? And one way to talk about the resulting function space of primitives is to define multiple polylogarithms recursively, as done here. Start with a shorter polylogarithm on the right-hand side and integrate it against the d log form, here this d log t minus a1. So with this recursive step, you build larger polylogarithms, and this space is by construction closed under taking primitives. So this is how you go step by step through open string punctures, if you integrate one at a time. And once you proceed to the last step of an open string calculation, you evaluate these primitives at special points, such as z equal to 1. So polylogs at special points, they now give you the promised multiple zeta values, which are the numbers that appear in the final answer for open string tree level amplitudes. So by evaluation, we pass from these iterated integrals to the nested sum representation of multiple zeta values. I guess you may know the Riemann zeta value the best, in case we just have a single argument n, that it's just a single sum over integer k to some negative power. And here, the Riemann zeta value is generalized to a nested sum over ordered integers k1, k2, dot, dot, dot. And the negative exponents of these, these are integers n, and they are determined by the kind of polylogarithm that you have evaluated. And this space of multiple zeta values is the most general coefficient in the alpha prime expansion of open string amplitudes. Perhaps somebody got nervous already that these integrals may diverge at the endpoints. So for instance, this g with a single entry 0 in front of the semicolon is by itself a divergent integral. And there's some experience to assign a regularized value in a way that the differential equation is preserved. And also the so-called shuffle multiplication is preserved. I didn't plan to go deeper into the details of that, but a lot of important structures expected for iterated integrals, they go through for the regularized versions. So don't be scared if you spotted endpoint divergence in this talk. Yeah, so this is the meromorphic story, polylogarithms from open strings on the disk. Let's now move on to closed strings on the sphere. And before telling you about single-valued polylogs, let me first point out the fundamental inconvenience of meromorphic functions. Namely, the meromorphic polylogs are notoriously multi-valued. You saw them defined through an iterated integral, and I didn't tell you about how the path is going. I just gave you the endpoints 0 and z. So you can ask, how does the polylog depend on the choice of path? And it only depends on the homotopy class of the path. It will change if I wind around the singular points. Like here in the right panel, this red curve with an extra circle around the singular point at z equal 1 will give rise to a monodromy. So this is an inconvenient multivaluedness in the meromorphic polynomial. But there are ways to remove these monodromies by adding complex conjugates. So here there's a super simple case of weight 1. Just add the logarithm with z bar in the place of z, and you have disposed the monodromy at weight 1. And now the good news is, also for polylogs at higher weight, for any number of integrations, you can also dispose the monodromies with a similar strategy. Choose some complex conjugate polylogs and put them together in a way that the monodromies are gone. And you can even preserve more than that. You can preserve the holomorphic differential. Here in the first line with the meromorphic in quotation marks, you see the differential equation of meromorphic polylogs, which follows by definition. And you can preserve that in the process of making the thing single-valued. And only for the holomorphic dz you can do that. You can't control the anti-meromorphic differential. This is a very general statement. If you insist on single-valuedness and a good holomorphic differential, you release control for the z-bar derivative. So there's a certain manual choice involved that we like the holomorphic side more than the anti-holomorphic side, because it's only one of the differentials that we can preserve. Okay, so the previous slide was about an existence statement. Let me try to get to a more constructive description. How can you build the explicit form of single-valued polylogarithms? So this was addressed by Francis Brown for the case of entries a equals 0 and 1. And Brown gave an entire generating series of single-valued genus 0 polynomials. So roughly speaking, you take the entries a1, a2, and so on, and then you split them. You deconcatenate the word formed by the a's, and put the first half into the meromorphic polylog, and then the second half of the word you invert and put into the anti-meromorphic side. And this is pretty good to eliminate the monodromies at the origin. And you need to go for an extra mile to also banish the monodromies at z equal 1. So you also need to add certain corrections with zeta values, which are completely determined by Brown's generating functions. And here I just want to give you one example to convey the flavor. Here in this weight 4 single-valued polylogarithm, you need to insert a term with a zeta 3 in it. Never mind the details of the formula, but you will later on see a one-loop version of that, where I also need a certain Zeta correction to maintain modularity. Good. And now that we have this family of single-valued polylogs, we can repeat the game of evaluating them. So remember, for the meromorphic ones, the choice z equal 1 gives you multiple zeta values, actually all of them. But now that we have improved our polylogs to be single-valued, we can ask again, what does now happen if we evaluate them at z equal 1? And the answer is that you get fewer multiple zeta values. So this is the definition of the single-valued subset of multiple zeta values. So for instance, when you used to get zeta 2 from a meromorphic polylog, and now you try it again to get zeta 2 from a single-valued one. Well, you will fail. You don't get it. The single-valued polylogs defined as above won't give you zeta 2. And this is
0 instead. I mean, there are constellations in these terms which produce 0. Or...
Oh yeah, indeed. It's cancellations between meromorphic and anti-meromorphic. So you can already see from the examples of depth 1, there's an alternating pattern. So the odd zeta values, they are enforced from meromorphic plus anti-meromorphic. The odd zetas get a factor of 2, whereas the even zetas, they are annihilated by cancellations.
It's confusing because there are only terms with positive sign in the definition of the single-valued polylog.
Oh yeah, the salient point is this inversion here, that So given that you invert the letters.
The relation between G and the elliptic zeta value as a -1.
Yeah.
Yeah, does it make sense?
Yeah.
Okay. Yeah, needless to say that more funny things happen at higher depths, like these double zetas. Well, it's much harder to write down a closed formula. I think it only exists for that.
Sorry, Oliver. So you define this single valued functions in this way, but there will be, because you wanted to preserve this fact that it satisfies this differential equation. But why do you want to choose that instead of some other definition?
Okay, yeah, this is also a good point. In the end, I could do the very same story with Z bar singled out. So there is a second space of single valued polylogs.
No, but I mean, why do you want to preserve this differential equation? This is my question.
Okay, yeah, in order
I just
to
wanted to start with some function and make it single valued. There will be many ways, I would imagine, not just this one. So
right. Yeah, so it's one way to understand how they arise in string calculations. You want to integrate finding a holomorphic primitive. You want to integrate functions on the sphere using Stokes' theorem. And then you can decide whether you do Stokes' theorem with a holomorphic primitive or with an anti-holomorphic one. So this is a string theorist's motivation. But also in mathematics, I think there are motivations related to the Hopf algebra structure, where you study the coaction of all these functions, where the derivatives play a prominent role. And there you want to maintain control on either holomorphic or anti-holomorphic derivative. Yeah, there's really multiple motivations.
You also preserve the shuffle product.
Oh yeah, indeed, the shuffle product is preserved by that single valued map, yes. And okay, there it wouldn't matter whether you preserve the holomorphic or
Sure, that's
yeah. Yeah, good point. Yeah, maybe this slide elaborates on a little bit more things of that. So ultimately, as I keep on claiming, these function spaces arise naturally in string tree-level amplitudes. So this is just to give an example. Suppose you're ultimately after a 6-point function, where the final homework is to integrate over 3 punctures. And here is the situation where you're almost there after integrating 2 out of 3. Only Z1 and Z2, but not yet Z0. Then order by order in alpha prime, you will get single valued polylogs of Z0. And to determine which of them, you can use Stokes' theorem and perform the Z1 and Z2 integrals by finding a holomorphic primitive. Primitive with respect to the holomorphic differential, which is at the same time single valued. So in order to render this process maximally clean and transparent, it's very useful to preserve the holomorphic differential.
So shouldn't there be a symmetry between Z0 going to Z0 bar? Will this be true of this single valued G?
This depends on which further single valued functions I put into the integrand. Remember, I had this blurry theory-dependent factor in an earlier slide. So this formula is to be understood schematically. In practice, you will have some rational functions, also known as Park-Taylor factors, that depend on Z and Z bar. And generically, they are not symmetric under exchange of Z and Z bar. The final amplitude is, but the individual building blocks that are well behaved are not.
I don't understand. What does this mean?
Yeah.
I thought you were literally computing these integrals and getting these functions, but now you're saying this is not true.
Yeah. So I'm hiding some theory-dependent details here, namely some denominators that you get out of the CFT correlation functions that you integrate.
But this will appear in this GSV?
Yeah, this will determine the ... in the GSV. I mean, there can be poles 1 over Z1 minus Z0. There can be other simple poles with differences in the punctures. So yeah, the details of what I'm hiding here will determine the ... So there are many choices what kind of SL2 covariant function I can put there. So I'm just highlighting the covariance factor, which is always there, which is coming from the plane waves of the vertex operators. But there are also some theory-dependent factors, like simple poles in both the Z's and the Z bars. Good. And yeah, so given that this next to last step is giving you single-valued polylogs at Z0, then the final integration over Z0 will ultimately evaluate these guys and land you on the single-valued subspace of multiple zeta values. This is a very heuristic cartoon argument of why you get multiple zeta values. I'm really omitting a lot of details. It's just to convey the flavor of these calculations. And you can look it up in great detail in the literature. In which way do you have to massage open string data? Which specific integration contours do you need to choose here to get closed string integrals with specific rational functions in the integrand? All of this is worked out to great detail in the literature. And the engine of this, of the proof for that is in knowing about the single-valued polygons. Okay, so after having illustrated how single-valued polylogs appear in string amplitudes, I should also point out that they have been seen in field-theoretic perturbation theory. Say, if you go to maximally supersymmetric gauge theories, n equal 4 super Young-Mills in the planar sector, there we have the notion of dual conformal symmetry, and the higher point functions can only depend on dual conformal cross ratios. And these cross ratios turn out to appear in single-valued polylogs if you go to the multi-Regge kinematics. So there is a great deal of applications of single-valued polylogs to the multi-Regge kinematics of n equal 4 super Young-Mills. And a lot of practitioners of that research line have also constructed single-valued polylogs in multiple variables. Multiple variables you need if you do 7 and 8 and 9 point functions of n equal 4 super Young-Mills, where the kinematic space in the multi-Regge limit is essentially a punctured Riemann field. That's more really the reason why the single-valued polylogs also appear in n equal 4. Good. So what was the moral of the last slides? I gave you a lightning walk through string tree level, pointed out that as you integrate one puncture after the other, you get polylogarithms, either meromorphic for open strings or single value for closed strings. And by killing monodromies, there's an intuitive way of running a single value map on polylogarithms. But in the last step, when you only have numbers, when you have integrated the last puncture, then you have zeta values, and it's less clear how you can assign a monodromy to a zeta value. But the good news is you can get an induced single value map for multiple zeta values by remembering that they come from polylogs. So in this way, the intuitive single value map for polylogs induces a single value map on the numbers on the multi-zetas. So that's one of the morals from here. And these polylogs are just an auxiliary object that were appearing in intermediate steps of the calculation. So the moral is it's useful to look at these intermediate steps. Even though they are not the final answer, they guide you in setting up the structure, they guide you in defining single-valued multiple zeta values. And I will next try to do something similar for genus 1. Is there any question about genus 0 before we proceed? Okay, let's go elliptic. So let's look at the closed string worldsheet for one-loop amplitudes, which has the topology of the torus. And throughout the talk, I will parameterize the torus as a parallelogram, where the two homology cycles, drawn in red and blue, are mapped to the unit interval and a straight line from 0 to tau. I guess the standard textbook parameterization. And when we constructed polylogs at genus 0, we were using the alphabet of logarithmic forms. We were using an alphabet of d log z and d log 1 minus z to construct the polylogs. Now at genus 1, you want to have an analog of these d log z's. So what's the alphabet of differential forms? And first of all, whatever these integration kernels are, they should better be good functions on a torus, in the sense that they should better have a double periodicity as you wind around the A cycle or the B cycle. And double periodicity doesn't come that easy. We will see on the next slide that you need to introduce a mild non-holomorphicity in doing so. And another thing to remark is that you will need an infinity of such integration kernels in order to catch all the iterated integrals on the torus. This is somewhat new, that there are infinitely many levels. Here there is an integer n labeling the integration kernels fn. And for different choices of these infinitely many kernels, you will have modular forms of different holomorphic weight. So here I'm referring to SL2Z matrices, to the modular group. So this is the first preview. We will deal with an infinity of integration kernels that are modular forms, just with holomorphic modular. And a neat way of defining these kernels is to write down a generating series. So this is the so-called canonical Isostat series that you see here. Never mind the details. It's schematically speaking a ratio of Jacobi theta functions. The odd Jacobi theta functions, to be precise. And we introduce an auxiliary parameter eta, which you find in the first argument of some of the theta functions. You might wonder if this is to be interpreted as a puncture on the torus, but we will degrade it to be just a bookkeeping variable. So eta will be abused to just be an expansion variable, and we can get a Laurent expansion from the left-hand side, and thereby define infinity of integration kernels, Fn.
The choice of eta is unfortunate.
Yeah, I think the same.
Oh, okay, yeah, you're right. It looks very n-ish. My apologies for that. Next edition of the slides will have a k in the place of n. Thank you. Okay, yeah. And yeah, here is a great result by Brown and Libby. With the infinity of fn's defined in that way, you will be able to span all the iterated integrals, the torus. And more precisely, these authors instruct you how to set them up in the homotopy way. So you do need all the infinity of fn's to get a closed system of iterated integrals, in particular elliptic polylogs. I was apologizing before that there's a mild non-holomorphicity coming in. I guess most of you know that story, that for the sake of double periodicity, you sometimes need non-holomorphic terms like the inz. And it in fact comes in a simple exponential for the generating series. And in case of the polylogs, our d log z forms all had simple poles. And here it's just a single f which has a pole, namely the f1. So almost all of these f's are regular. Good. So what can we do with these fn's? Now it's time to give you the details of how you get elliptic MZVs and elliptic polylogs in an open string setup. So here the intuition is that we place open string insertion points in a cylinder boundary, and we furthermore identify the cylinder boundary with an A cycle on the torus. And in this way, we get iterated integrals over the unit interval, since we are putting the A cycle on the real line. And by recursively integrating one of the kernels after the other, we can build a space of elliptic polylogarithms. And now you need slightly more labels as before in order to store the information. Where is the singularity in case of an F1, or which shift are you doing? This is an analog of genus 0. But you also need to store the information, which of the kernels did you just integrate? So these integers n running from 0 to infinity. Good, so these are the objects that appear naturally in integrating open string punctures, and the same would be true if I were to place some of the punctures on the other boundary. But these functions not only appear in string theory. In fact, the evaluation of Feynman integrals experienced a fantastic boost over the last years when these polylogs made it to the particle physics literature. And in fact, there are various formulations of elliptic polylogs, and yeah, it took a couple of years until the equivalence of different methods was established. But yeah, some flavor of these elliptic polylogs gamma shown here are ubiquitous now in the particle physics literature, and there are also fantastic contributions concerning their Hopf algebra structures, concerning their numerical evaluations. So this is a nice example how different communities are fruitfully collaborating.
Sorry, what is tau in the magnetic?
So usually tau is some kinematic variable or a certain combination of kinematic variables, say external momenta or masses in some dimensionless and Lorentz invariant combination. And if you have processes with several scales, several masses, several external momenta, then you can have polylogs in many variables. But usually these are not so simple functions of the kinematics. So I'm not sure whether I could write down an example on top of my head. Okay, to remind you, at genus 0, we first set up the polylogs, and then we evaluate it to get to multiple zeta values. And exactly the same story goes through here in the elliptic case. We have a variable z that keeps track of the endpoint of the integration path, and if we specialize z to be a nice point, like z equal 1, for instance, then the result resembles a zeta value from genus 0, and accordingly, these objects, polylogs and unit argument, are dubbed elliptic multiple zeta values by Benjamin Enriquez. And it's these elliptic multiple zeta values, omega, that arise in the complete configuration space integral for open strings at 1 loop. Still a function of tau, of the cylinder modulus, but all punctures integrated out. Okay, so maybe I should give you a little more details of why these elliptic polylogs are settling the open string 1 loop amplitudes. So first of all, the cylinder Green's function that we have in the universal Koba-Nielsen factor, the cylinder Green's function is just a special case of elliptic polylogs. In fact, a very simple one with just a single integration over the function f1. Okay, so this exponential here will keep you in the setup of elliptic polylogs. And then the theory-dependent factors that I keep on omitting, they will consist of these Kronecker-Eisenstein kernels Fn. So no matter whether I am in a bosonic theory or in a supersymmetric string theory, all the correlation functions of vertex operators give you polynomials in the Fn's. So these Kronecker-Eisenstein kernels, initially identified in the math literature, they are also favored by the conformal field theory for 1 loop string amplitudes when you put massless vertex operators on the cylinder boundary or the torus. And apart from these Kronecker-Eisenstein coefficients Fn, you sometimes get their special values at 0. Maybe that's something I could have mentioned before. If you evaluate these FKs at the origin, you get a good friend. You get the holomorphic Eisenstein series, denoted by a straight G here. My apologies if there are several G's in this talk. So whenever you see one of these script mode G's, it refers to a holomorphic Eisenstein series, the ring generators for the holomorphic modular forms. Good. But say for the purpose of the Z integrals, you can just pull them out. So it doesn't change the statement that you get elliptic polylogs and elliptic multiple zeta values after integrating over the cylinder punctures. Good. In order to get a little bit closer to a closed string and modular setup, let me mention a fun fact about the elliptic multiple zeta values. Well, we defined them as an iterated Z integral, integrating one puncture after the other as they appear in the definition of elliptic polylogs. But now we can do a funny paradigm shift. What if we trade iterated Z integrals for an iterated tau integral? It turns out that the tau derivative of elliptic multiple zeta values gives you the holomorphic Eisenstein series defined on the previous slide. So integrating back, you can write each elliptic multiple zeta value as an iterated Isostat integral, integrating over different taus. So maybe this is getting confusing if you are thinking too much about the geometry. It's a little bit like integrating over several versions of your torus or the cylinder. But I guess, yeah, from a purely mathematical point of view, no problem. Just take several holomorphic tau integrals with Isostat series in the kernels. And there are, strictly speaking, even some powers of tau that you should also insert to have a large enough set of kernels. It's always a similar game. You study iterated integrals, either in Z or in tau, and you need to make sure that you have a large enough collection of kernels to always find a primitive in the space you're working.
The case would be related to the NIs,
yeah, it's a four-liner formula. Ultimately, they are, but it's not so easy to make a general statement on how they are related. But yeah, the bigger the n here, the bigger the k there. I guess this is a safe statement. Good. Again, disclaimer that there may be some divergent integrals in here. For instance, if you remember that the holomorphic Eisenstein series has a zero node given by a power of pi, well, then you need to worry about an endpoint integral at the cusp, I infinity. And again, there is a well-studied regularization scheme, here known as tangential base point regularization. So thanks to the work of Francis Brown on that, we don't need to worry. So roughly speaking, the net effect of tangential base point regularization is that you discard the contribution from I infinity when evaluating the primitive.
So, the first definition is, of course, natural in string theory, whereas the second is kind of strange from string theory. Do you introduce it because it's useful in defining those functions, like it's more powerful or
oh, yeah, indeed.
than the first, or what is the reason to actually use it?
Yeah, a key motivation is that the upper description has a lot of hidden relations. If I write down different collections of n's, then there's a high redundancy. A lot of zeta values are proportional to each other or have some relations over the rationals and multi-zetas. But if you transform to iterated Eisenstein integrals, you see on the spot who is algebraically independent. But yeah, indeed, you are losing the intuition of integrating stuff on the cylinder boundary. This is fair to say. So in order to see their natural appearance in string theory, you need to study tau derivatives of various Koba-Nielsen integrals.
Oliver?
Yes, Eric.
Is there any relation between the tangential base point regularization and the usual story of truncating the fundamental domain as you have an integral along the imaginary axis, or is this just different?
Oh, okay, yeah. So far, I haven't found a direct connection. Maybe you are thinking of evaluating the non-analytic contributions to one-loop string amplitudes with a key contribution from the cusp. So far, I haven't managed to make a simple connection to tangential base point regularization.
Thanks.
Okay, so this finishes the walk through open string one-loop level. I've tailored the presentation such that we have a lot of synergies with the next chapter, which is closed strings at one loop. Any questions before we delve into that? So now this is the moment to introduce the modular graph forms, which are the coefficients in the alpha prime expansion of one-loop closed string amplitudes at a fixed modular parameter tau. So again, we are working on a fixed torus. We are relegating the modular integral over tau for later. And in order to integrate functions on the torus that are furthermore doubly periodic, it's highly useful to work with their Fourier representation. If we are dealing with doubly periodic functions on z+1 and z+ tau, then you can do Fourier expansions in two variables. Namely, we take the real variables u and v in the parametrization of the punctures as u tau plus v. So u and v are the real and co-moving coordinates of the torus punctures that we will integrate. And here are the main actors of the closed string integrals we are about to do. Either we are dealing with a Kronecker-Eisenstein coefficient from the theory-dependent factor, or we are dealing with a closed spring Green's function that you can write as a logarithm of a theta 1 function. And both have a super simple Fourier expansion or double Fourier expansion in these co-moving coordinates u and v. You get in both cases some infinite sums over the lattice of integers with the origin removed. Well, of course, the sum would blow up. So you can view it as an infrared regulated version of Feynman integrals on a torus, where, well, instead of a Feynman integration, we have a discrete sum over the momenta that are compatible with the torus. And in view of this tempting interpretation as Feynman integrals on a torus, I will use the notation P for these m tau plus n. So for these two integers m and n entangled with the modular parameter tau, and these plain waves from before, the e to the 2 pi I integer u, integer v, they will be identified with the Lorentzian inner product of the momentum p on the torus and the coordinate z on the torus. So here is a compact momentum space notation for the double Fourier expansions. So now, with this Fourier setting, we can now look at how modular graph forms are defined. So here I'm defining admittedly just a subset of them, but maybe it's nice to start from an expression which evaluates to an amplitude. So here is the monumental 82 result on the 4.1 loop amplitude of massless closed string states in type 2a and type 2b. So all the polarization dependence can be neatly pulled out. And the main work is to make sense of a scalar integral over the moduli space M14, where one modular integral is an order over different tori, and on a fixed torus, the contribution denoted by J here is an integral over the torus functions. And the integrand is again containing that universal Kober-Nielsen factor. And this is in fact everything. That theory-dependent factor is 1 here. So this is fully explicit and nothing hidden. So now in an alpha prime expansion, all you need to do is get a handle on integrals over Green's functions, over all combinations of Green's functions that are emitted by this exponential here. And again, the Green's function itself is this lattice sum, like an infrared regulated Feynman integral. So the homework is to integrate multiple lattice sums or products of lattice sums. And in each order of alpha prime, you have modular invariance on your side, because the Green's function is modular, the integration measure is modular, and of course, the overall contribution J for a given torus should be modular invariant. Yeah, since we have modular invariance order by order at alpha prime, this is a generating function of non-holomorphic modular forms. Non-holomorphic because the Green's function is non-holomorphic. Okay, so a little disclaimer here. You may be uneasy that we expand in alpha prime at a fixed value of tau. So strictly speaking, this will cut away certain non-analytic terms, some logarithms and Mandelstam variables. So this is a separate sector of the one loop string amplitude that can be studied using different methods. So what we are doing here is a power series expansion, which is tailored to get the effective action. And I can tell you more in private if you are curious about this non-analytic terms and how the separation is done. Okay, so as I was saying, let's integrate Green's functions. And even though we were looking at the 4-point function before, it may be good for generality to admit 5, 6, or more integrals. Let's pretend we are doing an n-point function and put any number of torus functions that you desire and see what kind of function space we get as we perform the integrals. For sure, modular invariance will always be there, no matter how many functions you integrate. And here is the reason why we speak of modular graph functions. Following the mindset of Feynman integrals on a torus, we will visualize the Green's function as an edge, mean, after all, the Green's function momentum space is 1 over p squared, absolute value. So each of these lines is standing for one Green's function, connecting the two edges here. And as we integrate over the vertices, we are just getting momentum delta functions in the momenta. This is really following the lines of doing a Feynman approach to correlation functions. So for instance, here, as we integrate a square of the Green's function, we just get higher powers of the propagator on the torus, higher powers of the torus momentum. And you can draw all kinds of graphs, and the simplest integrals or the simplest lattice sums arise if it's a one-loop graph. So the simplest slice of modular graph forms are those associated with an n-gon graph. Because we have so many vertices that impose momentum conservation, it's just a single lattice sum that survives. And this is known under the name of a non-holomorphic Isostat series, EK. So this is the simplest family of modular graph forms that are said to have depth 1, and that comes from one-loop graphs. So if we want to have more fun, if we want to go beyond the non-holomorphic Isostat series, the mission is clear: better introduce higher loops. So I hope it doesn't confuse you if I say loops. All of this is a fixed genus. Everything is happening on the torus, but we are putting a different network of Green's functions on the torus. This is how graphs of arbitrary loop orders arise. So the first step beyond non-holomorphic Eisenstein would be a two-loop graph. So with these dotted lines, I'm indicating that you can still concatenate many, many Green's functions. And the most general two-loop graph will then evaluate to a multiple lattice sum. Well, think by analogy with Feynman integrals. If it's a two-loop graph, then you're doing two integrals. And after accounting for the delta function up here, it's indeed a twofold lattice sum coming out of the two-loop graph. Yeah, so here I've chosen to maintain the symmetry under exchange of the three edges. That's why we have a delta function and one more lattice sums than actually present.
Yeah, it's a Kronecker, right?
Oh, okay, yeah, right. I should have said Kronecker delta. Yes, indeed.
From a mathematical point of view, there's the reason to take ABC to be integers, right?
Oh, that's absolutely fair to say. I think this is one of the most exciting follow-up research directions on the table, to explore how CABC behaves as a function of A, B, and C. Yeah, indeed.
So these kind of relations that we're going to show, they happen when they are integers. Presumably they would not be there away from those values.
Oh yeah, definitely. Maybe I should put a very big disclaimer that most of the material on this slide and the next ones is heavily tied to being integers, that ABC are integers. So if you insist that this is coming from a worldsheet, if you insist that this is coming from integer powers of Green's functions, then for sure these ABC parameters are bound to be integers. But you are missing a lot of important function spaces. So in the long run, we should, as Boris is saying, proceed to non-integer ABC. Yeah. But even in the integer case, there is some intriguing collection of relations among them. So the simplest case of such relations is if we study banana graphs. So if all you integrate is a power of the Green's function, then this corresponds to a banana graph with an increasing number of loops. So the bananas are the most aggressive way of increasing loop order, but nevertheless, it turns out that so many of them simplify a lot that you can rewrite the banana graph functions in a way that the right-hand side has a lower loop order. Like the two-loop banana boils down to a one-loop graph. Remember that E is non-holomorphic Eisenstein for a one-loop MGF, and accordingly also the higher loop bananas reduce to something of lower loop. And one of the key results of this talk is a way to manifest these relations, to predict that there must be such relations between different loop orders. I assume that I should be careful about the time.
Yeah, 15 minutes.
Okay, thank you. Okay, and yeah, as a step towards understanding why there are these relations between different loop orders, I will dress the MGFs in a different way. Instead of a lattice sum, possibly iterated lattice sum, we will go to iterated integrals. So this is now the moment where we reconnect with earlier parts of this talk. So I told you, for instance, that for open string set one loop, we have these elliptic multiple zeta values, which are iterated Eisenstein integrals. And in response to Guillaume's question, the advantage of iterated Eisenstein integrals is that they expose all the algebraic relations of E and ZVs. And to give the spoiler right away, if you want to achieve the same for the modular graph forms, to see all the algebraic relations on the spot, you should also go to iterated Eisenstein integrals. And here is how the details will work. So as long as we are on the open string side,
you go beyond linear relations.
Oh yeah, indeed, I go beyond linear relations. Consider, for instance, here the term here on the lowest line for the fifth power. Indeed, by algebraic, I really mean quadratic or polynomial relations. And the coefficients will be rational combinations of multiple zeta values. Okay. Yeah, so here is a first flavor of how modular graph forms will fit into the paradigm of iterated Eisenstein integrals. So similar to what you are doing for elliptic multiple zeta values, you can start from a holomorphic Eisenstein series and integrate it. And we already learned from EMs and Vs that you may need to adjoin powers of tau1, the integration variable. But modular graph forms have a lot of responsibility. They ought to be modular. And in order to improve the modular behavior of these iterated integrals, you tend to decorate the integration variable tau1 with these specific polynomials in the spectator variable tau and tau bar. So no worries about the tau bar. This is not the integration variable, so there's no issue with homotopy invariants. Okay, so step one is decorate the holomorphic Eisenstein series with some polynomial structure. And step two, we definitely need anti-holomorphic building blocks. After all, we start from integrating real analytic Green's functions that are symmetric under exchange of Z and Z bar. So accordingly, you need something anti-meromorphic, some complex conjugate holomorphic Eisenstein series. And again, there's a similar decoration as before. So here I'm labeling the depth 1 integrals over a single Eisenstein series by two numbers, J and K, where K is clearly the weight of the holomorphic Eisenstein series, and where J contains the detailed information about the polynomials. And if you want to describe the non-holomorphic Eisenstein series, so these one-loop graphs of the torus, then you should pick a special value of J equals K minus 1. So here is an iterated integral representation for the non-holomorphic Eisenstein series. And as I said, this object has the job to be modular invariant. And iterated Eisenstein integrals, they usually produce some impurities like zeta values. So you also need to add this zeta value here to compensate for the modular sins of the previous term. So this is similar to what we saw in genus 0, that every now and then, single-valued polylogs need corrections by zeta values. It's really like killing a tail of monodromies, of lower complexity terms.
So each of the blue and green integral would be separately in non-modular forms, which transform homogeneously, but then the difference between the two is very close to being modular once you add up this additional term.
But they are not holomorphic. What do you mean by modular?
Yeah, I meant in the general sense, in the sense that they transform inhomogeneously under the modular group. Because, because the contour from tau to I infinity would be mapped to some other contour as
I fully agree. Yeah, there's a lot of inhomogeneous behavior. Let's say the blue term by itself has a lot of inhomogeneities. And the green term will eat up a subset of these inhomogeneities. But there's still a surviving zeta value in the co-cycle with respect to modular S. So the leftover impurity is eaten by that term here. Indeed. I don't know whether it stands up to the definition of mock modular, but the point is that it's inhomogeneous how they transform. And I really don't want to flood you with formula, but I couldn't resist to show the depth2 example, mostly to point out a fun analogy to genus 0. So maybe you remember I told you about this construction of single-valued polylogs, where you mix holomorphic and anti-holomorphic in a certain way, that you rearrange the letters A, A1 and A2. And you can really start from the genus 0 single-valued map as a prototype to what you do with the iterated Isostat integrals. So the individual kernels are Isostat series with these polynomials, but the way how you combine them at the macroscopic level is just the same as genus 0. So if you know all the combinatorial structures from genus 0, you can recycle them almost literally to construct iterated Isostat integrals of higher depth. Or here, this is about real analytic combinations of iterated Isostat integrals that have a nice modular behavior, or at least as nice as you can get. Yeah, this disclaimer, as nice as you can get, is illustrated by the example here. So here is a two-loop modular graph form, C2,1,1. It's a double sum, if you wish, after evaluating the Kronecker delta. Oh. Thanks a lot. And having a double sum here morally corresponds to a double integral. So the most exciting term in the lowest line is the first one, where you have such a beta SV with two different integration terms. And again, it still has a slight modular problem. It transforms inhomogeneously under the modular group, and there's a tail of lower depth to compensate for these sins. And you can really view string theory as a machine who delivers these lower depth tails on the silver plate. We can milk out string amplitudes in order to anticipate what are the lower depth corrections that you need to add. Of course, you can also fix them by pure thought from a mathematical reasoning, but it turned out convenient to employ some string theoretic tools to fix all of these zeta values and negative powers of int tau. Yeah, so there was one elephant in the room that I didn't mention, Zeta corrections, but it's the same story as at tree level. I already told you about the tree level polylogs GSV, that they have certain zeta corrections that follow from generating series of Brown. And same story here for genus 1. There are again certain anti-meromorphic contributions that are needed to improve the modular properties. And in so many cases, we can just fix them by reality properties. So again here, string theory, which produces objects with known reality properties, is a good way of fixing these zeta corrections.
And the monom gets more and more complicated. Like here you get tau plus tau bar minus tau.
Yeah. There is an alternative language which is manifesting modular T invariants. I would need half a page of notation to do this in detail, but once you know the alphabet of modular T invariant objects, then this becomes very intuitive. So whatever these corrections are, they ought to be anti-meromorphic and modular T invariant. And this is asking a lot. There are not many possibilities. If you furthermore invoke transcendental weight conservation, then you can reduce the problem to very few parameters. Yeah, so I would need more notation to compactify this more, but yeah. Good. So I hope we are not getting lost in the details of this depth2 formula. The takeaway message, even if you forget about the definition of these beta SV, the takeaway message is that there is a natural way to combine meromorphic with anti-meromorphic iterated Isostat integrals. And you can nicely enumerate them by the modular weights k of the Isostat series and certain powers j that tell you about polynomial insertions. And this space of beta SV is guaranteed to contain all modular graph forms. Maybe you need some coefficients that are zeta values and negative powers of int tau, but other than that, this is the most general tau dependence that a modular graph form can have. And why the hell do I depart from these nested lattice sums? I depart from the lattice sums because there are relations that are pretty mysterious at the level of the lattice sums. So motivation number one is I use the beta as V because I want to expose all the relations. And motivation number two is that also the Fourier expansion is hard to get from a lattice sum, like the Q-bar expansion. And the beta SV have a relatively transparent Q series, simply because the holomorphic Isostat series have. And finally, we have a universal currency for both open and closed string quantities. Like EMZVs were meromorphic iterated integrals, and now we are promoting them to be real analytic and insert complex conjugates. So this is a way to make the closed string look like the open string. And indeed, you can really set up a single valued map. You can really design holomorphic objects beta such that the beta SV from the previous slides are their single valued images. I don't think I can say many details in view of the time, but roughly speaking, there is a proposal for a single valued map at genus 1 such that the beta SV is really the image of a meromorphic object, which gives you on the long run a path from the open string to the closed string, at least at the level of integrating the punctures. So this is a tentative genus 1 upgrade of a well-established single-valued map at genus 0. Good. I guess for timing reasons, I should skip a couple of slides. So what I'm skipping here is to say that you can also look at modular forms at non-zero modular weight. Also, this is contained in the beta SV. And other things that I probably skip largely, even though it hurts, is so-called elliptic modular graph forms. What if we don't integrate all the punctures? What if we keep one of the torus punctures unintegrated? Then the story is pretty similar. You get nested lattice sums, and they again...
Can I say something stupid? If I don't integrate one, by translation invariance, for me, I don't see anything. So what are you doing?
Oh, this is a really good point. Yeah, so indeed, insert the origin in your head as well. This is a really good point. Yeah.
Okay.
Yeah. So I really need one distance between 2 points that is left unintegrated. Thank you. Yeah. What I was about to say is, with one unintegrated Z0, you can still get nested lattice sums, but with a leftover Z dependence. And the pioneering paper is the one by Boris and Eric and Michael, who introduced a large class of them and did a lot of impressive manipulations. And yeah, one can generalize them in a similar way as has been done for modular graph forms. And also there you can meditate about their relations, the differentials in tau, the differentials in Z. And what you see from all of their differential structure is that they qualify as single-valued elliptic polylogarithms of arbitrary depth. So here, the gold standard is set by Zagier, who introduced single-valued elliptic polylogs at depth 1, certain lattice sums similar to the closed string Green's function. And what the elliptic modular graph forms do for their living is to generalize Zagier's polylogs to arbitrary depth, such that you have arbitrary numbers of Z or tau integrations as you explore different representations. And the way how Boris and collaborators first came across them is from degenerations of higher genus. So one out of the many motivations to study elliptic modular graph forms is that we want to have control, ultimately, over higher genus modular graph forms. And in particular, you need control over the boundaries of modular space, where the genus 2 curve degenerates like that to a torus with one more difference punctures. Good. My apologies for having skipped a lot and not done the best time management. So what I hope you have seen in this talk is a very mathematical approach to string amplitudes, where the integrals over the punctures with insertions of Green's functions, where they are used as generating functions for polylogs on various surfaces. And in particular, I try to advertise strings as a guidance and intuition on how to engineer single-valued objects, single-valued polylogs at genus 0, and modular forms at genus 1, where the modular property is the analog of the single-valuedness. And I very much hope that the same research program will be fruitful at higher genus. And if you want to get immersed into the subject and you want to have some help, either through a Mathematica package or through a nicely written PhD thesis, let me recommend these two works of Jan Gerken. And finally, one of the next steps is to connect with the mathematics literature. Francis Brown has studied non-holomorphic modular forms with very similar properties, a series of papers that was actually motivated by modular graph forms. And it's ongoing work to spell out the detailed dictionary between Brown's equivariate iterated Eisenstein integrals and the modular graph forms. Most prominently, these beta SV, which are used to manifest all their algebraic relations. Good, that's it. Thank you so much for your patience, and thanks to Biotech for allowing me to be here.
Time for a couple of questions. Yes.
So is the single value map useful in understanding double copy construction of closed string amplitude convolution?
Okay, double copy, yeah. Double copy is an alternative formulation of the single valued map. You want to have a way to foresee this part from there. So currently we have head start in knowing the single valued map, but we don't know a KLT formula at one loop. And it is likely to help us to find such a KLT formula if it exists. But from tree-level experience, there's a lot of expectations on what a one-loop KLT formula should be doing. So I'm not sure whether there exists a KLT formula out there that meets all the expectations. But I think...
But also naively, we expect, I mean, you construct closed string at one loop that's factorized as one loop times one loop bar, and this is not at all what your single valued map looks like.
Okay, so it's a double copy at the level of generating series. In some sense, you take a path-ordered exponential to generate the depth 1, depth 2, depth 3, depth 4 integrals. And you need to, in some sense, multiply two path-ordered exponentials in order to generate these cocktails of meromorphic times anti-meromorphic. So even though it looks like I'm doing additions here, I'm secretly doing a multiplication of generating series. And a technical headache is that there are multiple ways of arranging these generating series. So it was already a long story of trial and error to arrive in the beta SV as they are spelled out here.
Are there questions from people online?
Yes.
Eric, please go ahead.
So on this last point about the relation to Francis Brown's papers, it sounds like the functions you're considering fall nicely into the class of things he sketched. Do you have a feeling for how small of a corner of the space of relevant non-holomorphic modular forms for string theory these functions comprise?
Okay, yeah, so Francis is at least 2 layers of generality ahead. So in part 3 of Francis' papers, sorry I didn't reference it, there is a paper 1710 where he constructs cusp forms. And the cusp forms of paper 3, I don't know of any string theory appearance. Maybe I'm just missing it, but I'm currently not aware of a corner of string theory where to look.
Non-holomorphic cusp forms.
Oh yeah, indeed, non-holomorphic cusp forms. Thank you. But already when it comes to the non-cuspidal objects, Francis has also looked at holomorphic cusp forms and their iterated integrals. Like take Ramanujan delta, do an iterated integral, study their real part and imaginary part. And string theory doesn't like Ramanujan delta, at least as the outcome of torus integrals.
That is numerator.
Yes. Okay, and actually, if you build modular graph forms coming from Poincaré series, then you every now and then hit these iterated cusp-form integrals. So if you generalize modular graph forms by Poincaré series, then you can meet this more general space of Brown in the 1707 and 1708 paper, at least according to preliminary evidence at depth 2.
But isn't it by construction that those modular graph functions are the only thing that can appear in string theory anyway? I mean, considering string theory as just one loop, string theory integrant in closed string.
Yeah, I think that's fair to say. Yes. So these Poincaré series I mentioned, these are cases which do not appear in string theory. But let's say there's a certain intuition coming from Poincaré series how to complete the space. Not worrying if they appear in string theory or not.
So you mentioned that this integrated representation exposes all the relations. Do you mean to say that all relations between these polylogs, analytic polylogs, just come from the usual algebraic relations between holomorphic and series?
Oh, good that you asked this. Maybe you have a relation for G8 in mind, that G8 is the square of G4. Amusingly, this relation is not used here because we never have products of Isostat series at coincident points.
Okay.
For sure, you see two different factors of G, but they are always separated to be different integration variables.
So what do you mean? In what sense do they expose these relations then?
So they expose the relations in the following sense. The beta SV with different entries upstairs and downstairs, they are all linearly independent by a result of matrix. So if I rewrite each modular graph form in terms of this beta SV, I can just settle it by inspection, whether there's a relation or not.
Yeah, algebraically independent.
Algebraically independent, indeed.
Is that a motivic version, or here for the case of function, you can already prove that they are algebraically independent?
Oh yeah, here indeed, we don't even need a motivic setup to prove their linear independence, because you can really work with a series in Q. So this is a very hands-on method that Mattes was using here. Linear independence proof. Yeah. So here for the 3-loop banana from the 4th power of the Green's function, if you convert it to beta SV, then you get the same beta SV as on the right-hand side upon inserting, for instance, this expression here for C211. And they are generating function methods to express these covariance integrals as a series in beta SVs.
Very well, it's getting late. So just we thank Oli again for the last talk.